I'm considering this as A. This is a structure of A. This is A. Now, when you add HCl, you are going to get B and C. Now, let's add HCl on this. Now, H will come here. HCl will come here like this. H will be attached to this carbon. Cl will come out as Cl minus. This carbon will have a plus charge. Now the two products are given. That means one will be minor, one will be major. When Cl minus attacks this carbon having plus charge, that's the minor product. Because this is a 2-degree carbocation, after rearrangement it can turn out to be a 3-degree carbocation. So the one which is minor, that will be the one in which the Cl minus attacks this 2-degree carbocation. So one of B and C, now it hasn't been mentioned which is minor, which is major. So one of them has to be minor. But we know the structure of B because we know the structure of E. So we know D. From D we know B. So let's see. So one of the product will be this. This is C. This has to be C. The reason I'll tell you later, you must have understood by now because we know the structure of B. So this is C. Note it down. When you carry out rearrangement, suppose the carbocation is here. Now you are rearranging. That means there has to be a methyl shift. If you shift this methyl from here to this carbon, so if you bring out methyl anion outside, this carbocation will have a plus charge. Now this methyl will get added on this carbon like this. So now the carbocation is 3-degree carbocation and this is more stable carbocation. So the major product will be this one. Now when Cl minus comes and attacks the C plus and gets attached here, this is the major product. Fine. So this is B. This is B. Note it down. This is B. Now let's move ahead. From B you're adding alcoholic KOH. Now you're getting an isomer. Alcoholic KOH is a base. It will carry out elimination reaction here. It will abstract a hydrogen H plus from here. This will gain a negative charge. Cl minus will come out. This will gain a positive charge. C plus, C minus will form a bond like this. To write it properly, this is CS3. What is this? This is D. Fine. Isomer of A. Of course it's an isomer of A because it is also, just the position or the basic structure is different and it is C6H12. So it's an isomer of A. From on D, if you are carrying out ozonolysis, you are getting E. So let's do ozonolysis. So from both sides, you are going to get acetone from this side and you are going to get acetone from this side. And it fulfills both the criteria. It does not show Fering's solution test because it is not an aldehyde, it's a ketone. And it will show iodoform test because it does have a methyl group directly attached to C double bond O. We had this discussion before. Acetone shows iodoform test when we studied iodoform test. Now, on A, so from here it's all done. On A you are getting F and G. So this discussion we had, the structure of A gave aldehyde from one side and another formaldehyde from other side. So both are aldehydes, so both are going to give tolerance test and both are not going to give iodoform test. And now you are carrying out Cannizzaro reactions. So because one of them is formaldehyde, so it will have the attack of base first as we studied when we studied Cannizzaro reaction. So acid part is going to come from formaldehyde. So we are going to have a sodium salt of formic acid. And the other aldehyde is going to be reduced, and because it's an aldehyde, it will give a primary alcohol. That's it. Okay. Okay. Now we move on to the next reaction, and this reaction is called Bayer-Villiger reaction. Or Bayer-Villiger oxidation. In this reaction, this is the oxidation of carbonyl compound occurs, but the oxidation is not towards carboxylic acid. The oxidation results in a ester. For example, if I have a ketone like this, in this reaction we take a peroxyacid, RCO3H. Now this is a carboxylic acid. Fine. When we have a peroxy linkage in peroxyacid, when you have a peroxy linkage like this is a peroxy linkage bond between oxygen and oxygen. In this peroxy linkage, when the carboxylic acid has a peroxy linkage, it is called as peroxyacid. Fine. So in this reaction we take a peroxyacid. When we take a peroxyacid, then the final product is this. Oxygen is inserted between carbonyl group and R group, and that results in an ester. And this peroxy acid is reduced to carboxylic acid. Like this. So the acid part is coming from this peroxy acid. This peroxy acid will be reduced to carboxylic acid, and this carbonyl compound will be oxidized to ester. Now because there are two possibilities, there are two bonds. One possibility is insertion between carbonyl group and R dash, other is insertion between carbonyl group and R. Now here, whichever group has higher migratory aptitude, insertion will be between carbonyl group and that group. Here we have considered that migratory aptitude of R dash is greater than R. If the migratory aptitude of R would have been greater than R dash, then the insertion would have been between carbonyl group and R. So when we will solve problems, it will become more clear. For now, whichever group has greater migratory aptitude. And just to remind you very quickly, the group that is more bulky, the group that is more electron rich, that group has greater migratory aptitude. The exception is hydrogen has highest migratory aptitude, even though it is not bulky, even though it is not electron rich. The reason for that is small size, so the mobility of that hydrogen is very high. Otherwise, apart from hydrogen, for all other groups, the more bulky the group, the more electron rich it is, and the more electron rich it is, the higher migratory aptitude it will have. Fine? Alright. So that's what happens. Let's see the mechanism, how it happens. Now this is the structure of peroxyacid. There are 3 hydrogen, 1, 2, 3. Now you have to quickly identify which one is most basic. Now this oxygen number 2 is not basic at all, because the electron of this oxygen number 2 is delocalized into the orbital of oxygen number 1. There is ongoing resonance between oxygen number 1 and oxygen number 2, or oxygen number 2 and C double bond O. So the electronic wave of oxygen number 2 is pushed into the oxygen number 1. That's how resonance occurs. If you draw one resonating structure, the resonating structure will look like this. As you can see, oxygen number 2 has partial positive charge in the hybrid, and the electrons have been pumped into the orbital of oxygen number 1. So oxygen number 2 is not basic at all. Oxygen number 1 has sp2 hybridization if you check. 1 pi bond. Oxygen number 3 has sp3 hybridization if you check. No pi bonds. So oxygen number 3 is the most basic site here. So if some attack has to occur, that will occur from oxygen number 3. Fine.